Today we'll start talking about the Sylow theorems. Let me first recall two results that we spoke about in our previous videos. So the first one was the proposition we started out with, which is that if G is a group which acts on a set X, both G and X being finite, and if G turns out to be a P group, P is a fixed prime, and X is the cardinality of X is not divisible by P, then there exists a fixed point for the action. Okay, and the set of fixed points is non-empty. So this was the first thing that we proved by analyzing orbits and stabilizers and so on. The second one is was one of our applications of this basic fixed point principle, which said that if I take any two numbers n and r, natural numbers, then the binomial coefficient Pn choose Pr is congruent to the binomial coefficient n choose r modulo P. Okay. So these were two of the results, and I'm sort of recalling them specifically because I'm going to use both of them together. So let's begin. So what I first want to ask is sort of the following converse, if you will, to this proposition here. So here's a converse question. So converse to this proposition. So maybe we should just give this a name for now. Let me call this proposition A. So I want to know, what can I say about the converse to proposition A? Is there a converse? Okay. In other words, can I say something about suppose I have, so okay, let's try and formulate a reasonable converse here. So let me make some hypotheses. So let me call this proposition B. So again, I'll make these blanket assumptions that P is a prime, G and X are finite sets, and G is a group acting on the set X. So for proposition B, let me formulate it as follows. Let P divide the cardinality of G first. Okay, so let me assume that the group cardinality is divisible by P. Now suppose we have the following property, that whenever this group G acts on a set X whose cardinality is not divisible by P, then it always has fixed points. Okay, so it acts in such a way that it always has every action on a set whose cardinality is not divisible by P, every such action has a fixed point. Okay, so suppose the group has this property. So let P divide the cardinality of G. Suppose it is true that for all finite sets X, so let me call it finite G sets, recall that means that there is an action of the group G on the set X. Suppose it is true that for all finite G sets X such that P doesn't divide its cardinality, we have Xg is not empty. Okay, in other words, every such action has fixed points. Then can I conclude that G is a P group? Then G, I want to claim, is in fact a P group. Okay, so observe, if G is a P group, then this is the proposition A says exactly this. I mean, it says that on every such set X whose cardinality is not divisible by P, the action of G will have fixed points. Okay, so we are sort of asking the converse question. If we know this property, the fixed point property of actions, then is it necessarily true that G is a P group? Okay, and for this, of course, I will assume that P divides the cardinality of G. That's sort of the first main assumption. Okay, we will prove this statement by sort of first rephrasing it. So it turns out that this is in fact true, and let's prove this. To prove this, let's rephrase it in its contrapositive form. So what does that mean? We will show, suppose G is not, so in some sense proof by contradiction if you wish, suppose G is not a P group. Okay, but remember the cardinality of G was divisible by P. So if you write out what the cardinality of G looks like, P will be one of the factors. Okay, and of course it can occur to some power, right? Cardinality could be divisible by P, P square, P cubed, and so on. There will always be some highest power of P which divides the cardinality. So let me call that D. So what is D here? D is the highest power of P such that P power D divides the cardinality of the group. And of course if I write out the prime factorization of G, of the cardinality of G, in addition to P power D, then what I will start seeing next is a bunch of powers of other primes, not P itself but other primes. So let me not write out the entire prime factorization. Let me just call that product of powers of other primes as the number m. Okay, so what is m here? Well, m is a number that's at least 1, and observe m is essentially the product of prime powers other than P. So of course m is co-prime to P. In other words, P doesn't divide the number m. Okay, so any number can always be written in this way, but I still haven't incorporated this assumption. I'm saying suppose G is not a P group. So what does that mean? It says when I write the cardinality of G in this way, the number m cannot be 1. Okay, so if the number m is 1, then of course it just means that the cardinality of G is P power D. Okay, so here's what I know, that m is not 1, m is at least 2. Okay, so this is what we conclude from the fact that, from the assumption that G is not a P group. Okay, now let's see what do we need to do in order to prove the proposition. So let me go back to the statement of proposition B. Okay, so it says suppose it is true that for all finite G sets X such that P doesn't divide the cardinality, we have Xg is not empty, then G is a P group, right? So to prove this, I'm saying suppose G is not a P group, then what I will do is I will produce a finite G set X. What we need to do is to produce a finite G set X whose cardinality is not divisible by P such that Xg is empty. Okay, so this is what we would need to do in order to complete the proof. So need to construct a finite G set X with P not dividing its cardinality and such that there are no fixed points. Okay, if I can do this, then I would have obtained a contradiction, and therefore my original assumption would have been wrong, and therefore the proof would be complete. Okay, so what I really need to do is the following. So if G is not a P group, then I should be able to construct an action of G on a set X such that there are no fixed points. In other words, I need to construct a fixed point free action. Okay, so such an action, let's just give this a name. So I would like to say that this sort of action is what's called fixed point free, meaning there are no fixed points here. Okay, or fixed point less if you wish. Okay, so let's analyze such actions for a little while. So notice the key point here is we also need this condition. There are two conditions we need to satisfy. Number one, the cardinality should not be divisible by P, and secondly, there should be no fixed points. Okay, now so this condition is what I want to call fixed point freeness. Okay, now what's the next thing? Let's show that okay, so let's analyze fixed point free actions for a little bit. So what are some examples of fixed point free actions? Examples of fixed point free actions. Okay, so let me assume my group G is fixed. So G is my given finite group. Now there's always a very nice action which we have looked at before, which is a group acting on itself by sort of left multiplication, by multiplication. So how does the group G act in this case? G acting on the group element G1 is just the product G1. Okay, so here G and G1 are both elements of the group. So the group and the set are in some sense the same. So I think of this as my set X on which my group acts. This acts by left multiplication. And the interesting thing about this is that this is a fixed point free action. Okay, so let's check that. What are the fixed points for this action? So if I have a fixed point, so suppose let me call an element G1, let's say, if it is a fixed point for this action. If I have a fixed point, then what does that mean? It says that G acting on G1 is G1 for all group elements G and G. Okay, but that just means that the product G1 equals G1, but this necessarily means, and remember this should hold for all group elements G and G. Now what does that mean? That just means that, well, I can, after all it's a group, so I can cancel, I have cancellation on both sides, so it means G must be the identity element. Okay, but remember this equation is supposed to hold for all group elements G and G. Okay, but what we have just shown is it can only possibly hold for the identity element of G. Okay, so observe, but remember we know that G is not the identity group. Remember that G is not just an element, the group with a single element, since we have already assumed that it's divisible by some prime number, right? So this is, in other words, cardinality of G is necessarily 2 or more. So surely there exists an element other than the identity in the group. Okay, therefore I can always find an element G in G other than the identity. Okay, and also for that element I get a contradiction here. Okay, so therefore I can't have, so what do I mean? There exists an element G in G, so that G is not equal to 1. For that G1 cannot equal G1. Okay, so therefore G1 cannot be a fixed point, therefore G1 cannot be. Okay, so in other words, I cannot have any fixed points for this action. Okay, so therefore we conclude that under the hypothesis that the group is not the identity group, the left multiplication action is fixed point free. Okay, so this is one example. Now here's another important example that will come up again. So this has already occurred in our previous video. So this is what we had called action on subsets. Okay, so what is the general setting here? If I have a group which acts on a set X, then from this I can construct a new action of the group G on subsets of X. Okay, so on the power set, what we call the power set of X, this is the set of all A such that A is a subset of X. Okay, so I can construct an action on subsets, and what's the action? Well, it's just the element wise action. So recall again that the action on subsets is defined like this: G, a group element acting on a subset A. So here A is assumed to be a subset of the original set X. How does G act on this subset A? It just acts element wise. It's the set consisting of G dot A, where A ranges over all elements of A. Okay, so this is going to be a new subset, and this is the action. G acting on A produces this new subset, which is just the element wise action on the original subset. And observe, we had used this in fact to prove that the congruence that Pn choose PR is congruent to n choose R mod P by sort of analyzing the action on dots in a grid and looking at subsets of dots and so on. So this is a general formalism. Whenever you have an action on a set, you also have automatically an action on subsets of that set. So let's apply this to the particular case. So let's take the example of the previous action. Suppose I take my set X to also be the group G. Okay, in other words, I look at G acting on G by the multiplication, by left multiplication. Now this action, well, what are its, well, okay, now I want to look at the action now on subsets of G. So for the action on G, I've just said there cannot possibly be fixed points. But what about for the action on subsets of G? Can I have fixed points there? Okay, So let's analyze that action. So let's call this new set as y maybe. Now let's ask, what is yg? In other words, which subsets of G are invariant under this action? Okay. So let's observe what do we have. So suppose I have a subset. So suppose I have a fixed point. Then what property must that fixed point satisfy? Then it means G dot A must equal A. This should be true for all group elements G and G. Okay. In other words, on the left hand side I have the product GA as G belongs to G. Sorry, as A belongs to A, as A ranges over A, and on the right hand side I just have the original set A itself. Okay. Now what does this mean? So this is the property I want to be true. So maybe it's easiest to just draw a figure here. So let me imagine this is my group G. Okay, and I have a certain subset A of the group. So here's my subset A. Now what I'm saying is that if I take these elements of A and I multiply all of them by a single group element G, no matter which one, the answer is again the same dots. Okay, meaning when I hit this dot by an element of G, it could become some other dot. Okay, but it doesn't leave the group. So it doesn't leave the subset A. Okay, so when I multiply G with elements of A, I just get back elements of A again. Okay, so that's sort of what this is saying. Okay, now observe again that this is very easy to violate. For example, suppose I take an element B here. Okay, so here's my conclusion. Let's analyze this. Suppose A is not the whole set G. Okay, then pick some element B which is outside A. Okay, so that's in the green dot in the picture, a point which is not in A. Now observe that suppose I take any point A in A, I can always map it to B. So let's call this, take any one point A in A. I claim you can find a group element which will, when acting on A, it will give you B. Okay. Now observe, there always exists a group element G in G such that G, when acting on A, will give me B. Okay, and why? Well, that element is namely the element G equals B A inverse, right? Because recall, this action of G on A was just the action by left multiplication. So if I multiply A on the left by B A inverse, of course the answer is B. Okay, so if I take this particular group element G, it maps A to this element B which is outside A. Okay, so what does that mean? It says that there cannot really exist any subset A which is a fixed point for this action. Okay, because I can always find an appropriate group element which will take a point A which is inside this subset to a point B which is outside this subset. Okay, so what does that mean? This means, observe, A cannot be a fixed point. Okay, so this was under the assumption that A was not the whole set, right? So this analysis, you can try and convince yourselves that this analysis actually proves the following. So here's our conclusion. It says that if I have any proper non-empty subset of G, it cannot be a fixed point for this action. In other words, the only fixed points are, well, the empty set is a subset, and it's a fixed point, of course, because if it's empty to begin with, when you act by the group elements, there is nothing you can act on, so the result is again empty. Okay, and the whole set G, that's again invariant because that's a fixed point, because when you hit every element of the group G by some fixed element small g, what you get is again elements of the group G. Okay, so it's trivial that the whole set is necessarily a fixed point. Okay, so here's the conclusion. There are only two fixed points for the action on the power set, which is the empty set and the whole set. Okay, so this is almost fixed point free. It's not quite fixed point free. There are these two sort of trivial fixed points, but there is this sort of example 3 is a slight modification of this earlier argument. Let's consider not the entire power set. So let me call this this set instead of the set y. Let me fix also a number. Okay, what shall we call it? Let's call it so I have the cardinality of the group here. So remember, the cardinality of the group was something. We assume the cardinality of the group looks like this, p to the dm. Okay, so let me pick some number k between 1 and strictly smaller than the cardinality of the group. Okay, or maybe the sort of a symmetrical way to write it is, I take k to be a natural number which is strictly between 0 and the cardinality of the group. Okay, then look at what I'll call y sub k. Okay, so let's define this set called y sub k. Well, what is this? So maybe another notation. So let me also give another name for this. It is the p, so the power set of g with k as my subscript, pkg. So what is pkg? It is the set of all subsets of g whose cardinality is k, okay, of a fixed cardinality. And again, remember, this is again something we have seen in the earlier video on the congruence problem, where we took all dots. So we took a grid of 12 dots and we looked at all subsets of 6 dots out of the 12 dots. Okay, so we fix a cardinality of the subsets and observe that there is of course a group action also on pkg. Okay, so observe g acts, the action on subsets also gives you an action of the group g on the set pkg. Okay, so there is an action of g on pkg. Y the same thing. So how does it act? When g acts on a subset A, it just gives you the element wise action, which in this case is just left multiplication. So let's just write it as GA, the product as A belongs to A. And this new set of course has the same cardinality as the original set, because I've just taken element by element and acted on them by left multiplied by group element G. So this is just going to give me the original thing. Okay, so if the original set had k elements, the new set will have k elements also. So it will be another element of pkg. Okay, so what I have now is the action of a group on subsets of cardinality k. Okay, and now observe that if k is strictly between 0 and cardinality g, okay, then what does that mean? It means that the subsets A that I am considering here, so pkg, the subsets A, if I took k equal to 0, then p0 is just it contains only the empty set. And if I took k to be the other end, mod g itself, then the only subset in pkg will be the full set. Okay, now for k strictly between these two bounds, I have pkg consists of subsets which are non-empty and not the whole proper subsets, and we have just seen that none of those can be a fixed point. Okay, so observe by what we have just said, so by this observation before, by observation star, it follows that for k strictly between these two numbers, pkg has no fixed points. Okay, so here's a fixed point free action, has no g fixed points. Okay, so we have managed to find an example of something which has no g fixed points. And remember, however, that, so let's go back to what we wanted to prove. We wanted to prove that there exists a subset, need to construct a finite g set x such that there are no fixed points. So that we have managed to do now. Right, take a group G and look at pkg, for example, where k is any number between 0 and mod g. That's a fixed point free action. But remember, there is this additional condition. I also want my set to have cardinality that's not divisible by p. Okay, so now let's look at this set that we have managed to construct right here, which is what I call pkg. So now what can I say about the cardinality of pkg? is it divisible by p or not? I would like it not to be divisible by p, right? If I can find a value of k, for some value of k, if this is not divisible by p, then I have done, I have proved my proposition. Okay. For let's just say, for what value of k is it not divisible by p? Is there a value of k? So is there a value of k for which the cardinality of pkg, let's make ourselves more space, so is there a value of k for which the cardinality of pkg is not divisible by p? Okay, and to answer this we need that second observation that we talked about. So let's ask ourselves, what's the cardinality of pkg? Well, that's exactly cardinality of G, choose k, right? Number of ways of choosing k elements out of mod G elements. And remember, what's the thing on top going to look like? It's p to the dm, that's the what we assumed is the cardinality of G, choose k. Okay. Now what I want to do is to try and use that proposition. So let me take the following value of k. So let me take k to be let's say p, for instance. Okay, so I mean we could start with various choices of k, but let's take k to be, well, maybe how about k equals 1? That's the most obvious choice, right? So let's try a few values of k. If you take k to be 1, then this is p to the d choose m, p to the d m choose 1, which is p to the d m itself. Well, this is divisible by p because there's of course a p to the d in front, right? So that's no good. That value of k is not going to help me. Let me try the next one, which is p itself. Well, I'm going to try p. Now look at this. So p to the dm choose p. So I will put this into the form of the earlier result. So it is p to the dm choose p into 1. So I will write it as p times p to the d minus 1 m choose p times 1. Okay, and which by the earlier result is congruent to p to the d minus 1 m choose 1 mod p. Okay, now let's look at this. It's p to the d minus 1 m choose 1, but that's just by definition p to the d minus 1 m mod p. Okay, and now this again is, well, this is could be 0 mod p because p to the d minus 1 is probably still some, some power of p. But it's already better than the original, right? The original guy was p to the dm. Now I managed to get it down to p to the d minus 1m. Okay, and now you can see that all it takes now is to repeat this argument. So let's repeat this argument. The value of k that will do the trick for us is p to the d. So here's the chain of computation. So if I have p to the dm choose p to the d, I can think of it as, I'll pull out a p from both, p to the d minus 1m, p to the d minus 1, and by that proposition, by that result, it's p to the d minus 1m choose p to the d minus 1. Okay, mod p. Now again, this is in the same form as the original. I can keep going, therefore. Again, I'll pull out a p from both the thing on the top and on the bottom, and I will get this to be p to the d minus 2m choose p to the d minus 2 mod p, and so on and so forth till all the p's have been pulled out one by one, and what's on top is m and what's on the bottom is 1. So this is m choose 1 mod p, which is of course just m. Okay, so observe this is nothing but m mod p. Okay, so what have we proved? P to the d m choose p to the d is congruent to m mod p, and m, remember, was a number that's not divisible by p. Okay, so but p doesn't divide m. That was our assumption. That's what m was, and m was a number that was 2 or more. Okay, so what does that mean? I mean, I don't really care about no, I do. So let's say m here is a number that's 2 or more. That was our assumption that G was not a p group. So this means that this number p to the d m choose p to the d is congruent to a number that's not, so it's not congruent to 0 mod p, it's not divisible by p. I mean, at the moment, let me not worry about this m greater than or equal to 2 business. So all I care about is that m is not divisible by p. Okay, that means that neither is this p to the d m, choose p to the d. Okay, so what have we done? We have actually managed to do what we wanted, that we have constructed, we seem to have constructed a set on which this group G acts without fixed points. Okay, therefore final conclusion is the following, that under the assumption, so if G is not a P group, look at the set, the power set of G, subsets of G of cardinality exactly P power D. Okay, so let's say cardinality of G looks like P power D times M. Okay, P doesn't divide M. Then what we have shown is that the action of G on this set has no fixed points. Okay, but we seemingly haven't used the fact that m is at least 2, but we actually have used it. So observe that I also assumed, so G can be written in this way, P naught dividing m is at least 2, right, because it's not a P group. Where have we used it? So observe, this has no fixed points, that requires that remember what did I say before? I said the power set pkg, the action of G on the power set pkg has no fixed points, provided k is strictly between 0 and the cardinality of G. Okay, so I need this strict inequality here. Okay, now why is that inequality strict in this case? So if I take k to be P to the D and mod G is P to the dm, now this inequality is strict because m is at least 2. Okay, that's why it's true. So I'm actually looking at proper subsets of cardinality of P power D are actually proper subsets of the group. They are not the entire group itself, because P to the D is in fact strictly smaller than the full cardinality of the group. Okay, so therefore we have managed to prove, therefore this proves proposition B. Proposition B is proved. In other words, we have managed to prove a nice converse to our original result. So let me go back and show you the statement of proposition B. So here's what we have managed to prove. Okay, which is that if a prime divides the cardinality of a group, and suppose it's true that for all G sets X such that P doesn't divide its cardinality, there is a fixed point, then this group had better be a P group. Okay,